Hello and welcome to the newest edition of Advanced. Any answers? Anybody look at it? No? Harry? Okay, never mind. Do you know what the question is, or shall I say that in different words? Or in the same words?
So I get what he's asking.
Okay, so we had these three versions of the shortest path thing. And there are some clear ways in which you can use one of the versions to solve the others. So it sort of seems that this is the hardest to solve in some sense, because when you can solve this one, when you have an algorithm that gives you the shortest path, then it's easy to calculate the length. You just add all the values along the shortest path. And when you can solve this one, then it's easy to solve this one, because you just find the short value, just find the length of the shortest path and you compare it to the number that you're working. And the question is, can you go back from this one to that one? Okay, so if you have an algorithm that solves the decision problem, can you solve the value problem as well, the optimization value? Not quite the full. Maybe the full is out of scope, but maybe this one you can solve. And so the hint that's given in the question is that you should be able to do what's called a binary search. So for example, you can kind of play a guessing game. Okay.
It's hard to do with changing the integer k.
And that's always possible with any kind of optimization problem. So yeah, exactly. So you can use the what do I call it? Decision version algorithm as a black box. Okay, which is an expression which means that you just well, you have it and you don't care what's inside, and you ask a question. So you can start with some large number that you know that the shortest path is certainly shorter than. Okay, so for example, I'll start with a large A. For example, you can add all the edge lengths. Yeah, so when you add them all, you know that certainly the shortest path is not going to be longer than that, because it's not going to use not going to use any edge twice, because why would it? It would that would mean that it got it wrong at some point and had to come back to the same place and then take the right one, and then it would just take the same one to start with. So this is certainly going to be, so now to ask black box whether the shortest path is, well, length at most k. Okay, and if it says yes, if no, there is no path at all. That is also a possibility. If yes, so that's number one, number two, number three, number four. Yes. Oh no. It's not number one, number two. Well, okay, number one, number two, number three, number four. If yes, to what? Put. So the new k will be half of the old k. And if you're asking for an integer, then you can round it any way you want. So say you round it up. And then I wrote it the wrong way, so I have to. So ask again. Ask the black box whether the shortest path. I'm not writing it in there. Is at most this new k. If no,
I need to go back. There's a bit value between the one that's feasible and the one that isn't.
and okay, this is not how you would write the algorithm, but I just made messed it up. I didn't prepare it written out. Sorry. So okay. So if no, you have to go back. So it's kind of say if no, you want to go up. So you want to take something that's halfway between the current k and the old k, and you can round it any way you want. So you round it up. I might round it down. And if yes, then you want to halve it again. So you to round it in some way, and then it's roughly how it works. If you know the length now, stop. Otherwise, repeat from 5. Okay, this is a very badly written algorithm, but you get the idea. Do you? So kind of you want to know, let's say the whole sum is something nice like 120, and it starts at 0. So I put down a number here, and okay, I'm thinking a number of the shortest path. It's kind of like you're guessing the number. Okay, you're trying to make as few guesses as possible. This is the best way to do it. So you ask, is it less than or equal to 120? And I've put a number down here. You can't see.
I can't see it because of this. It's okay.
Doesn't matter.
Anyway.
So you ask, is it between 0 and 120? And I say yes. So you divide 120 by half. You don't divide it by half, but divide by 2. So you divide the interval in half where you know the value is. You ask about 60. Is it no more than 60? And I say, yeah, it's no more than 60. Okay, so the algorithm tells you divide again. And you ask, is it no more than 30? Okay, and I say, no, not true. So you go halfway, and then this tells you to go to 45, which is right in the middle, between 30 and 60, right? And I say, yeah, it's less than or equal to 45. So, so you don't want to divide by 2. So this is wrong.
Oh, because when it goes, it doesn't remember the previous step. Because if you carried on from there, it could go down to cut off at 22.5.
I think you have to remember.
It has to remember the previous constraints, doesn't it?
It has to remember the interval in which we currently know it's in.
Because otherwise it just goes, is it goes to 45?
Yeah, so
yes.
that's stupid. Okay, so I need to fix this. So we found an error in when I looked at the algorithm. But well, the idea is should be clear. So I'm not keeping old k. I'm keeping so a is 0. Is old k. It's a more old. See, it's good to discover errors. This is how it actually works now. We'll go to that. So what needs to be done? Okay, so if no, that means it's in the larger bit, right?
Mm-hmm.
So what you want is you want to move the lower bound. So the idea is we always know so the idea is that we know that the right value, the correct value, is in a B. Okay. And that interval. So if no, you have to move so k is right in the middle of that interval. Because I've got a, b is k, and then I after k. So k is right in the middle. So we have to move no, then a is k plus 1. And if yes, then b will be k. And we're still know that we're between a and b. So if you know the length now, means okay, if a equals b, then we can stop. Otherwise, put k. So k should be between a and b, halfway, and repeat. Okay, are you both happy about this? Yes. So now, okay, so now I'm asking about 45. Now I know it's somewhere between 30 and 60, so I'm asking about 45. And my answer is, yeah, it's at most 45. So I go, now I know A and B is, so 75 divided by 2 is 38. Round it up. This is telling me to try 38, and it's still good, so it's going to try 34, and it's still good, so it's going to try 32, and that's no longer. Okay, so now I've got 32, 34, and I ask about 33, and it says yes, so I know 32, 33. And so it's telling me to ask about 33, and I say yes, so I can move A to 33, and then D is 33 as well. Yeah, something like that. Okay, so we've got 33. Okay, so this is the algorithm, and it runs quite efficiently, sort of. So how many times do you have to do it? The black box. Okay, 7, but 7 is 7 or something like that, thereabouts. So if this is n, how many times do we need to run the black box if the starting number is n? Uh-huh. This is basic problem solving maths. So in the beginning, we have about 120, well, maybe 121 different values. And then what happens with the number of possible values every time we ask a question? We halve it. How many times do we have to halve it to get 1?
Not functioning today. It's not working. Stuff out.
Okay, let's, so if you don't know, let's have a look at it backwards. Okay, so we end up with 1 possible value. In the previous step, we had how many?
2.
In the previous step, we had how many? Thereabouts. So we have to double it every time. How many times do we have to double it to get n?
So
Yeah, for a general n.
it's 2 to the power of n until it exceeds what n is. It's 2 to the power of something until it exceeds what n is. You know what I mean?
No, I don't. Yeah, so if you do it t times, how many different values do you get?
2 to the t.
2 to the t. So we want t which satisfies t such that 2 to the t is, well, greater than or equal to, let's say, equal to n.
I was working it forward. That's what I was trying to say.
Yeah.
I was just wording it forward.
So yeah, so what is the t?
Oh, wait.
This is A-level maths. This is GCSE maths. No?
It's not happening.
It's called the logarithm.
Yeah.
I would really expect first year students to know what the logarithm. So it's kind of.
Yeah.
So we need to run it. black box. Log to n rounded up times or thereabouts. Which is good. So with these things, the thing is, if you want to have a polynomial, so if you just look at, if you get the shortest path and the graph structure and all that, if you want a polynomial time algorithm that takes an input number like that, then you need a logarithmic number of iterations, because the number, the length of a number is logarithmic in value of the number. Because, you know, for 120, you use 3 digits rather than 20 digits and so on. So if you, every time you multiply by 10 the number, you only add 1 digit. Not the kind of thing. But anyway, so this is a polynomial time algorithm, and yeah, and it works. And yeah, that's the answer. There's half of the lecture gone. We haven't even started doing anything. Okay, so let's start it. So it's a little puzzle.
It's a map.
Yes. I don't know why they put the lake there in Hungary. They didn't put any other lake.
You got the one in Turkey.
One in Turkey. Oh, okay. It's covered by screens. Okay, so do you know about the 4-color problem?
This is that thing of trying to put colour every country in, isn't it, without having two colours touch each other.
Without having 2 countries of the same color touch each other, yes.
Yeah.
Okay, can you do it? Well, just do it. You've got the map.
What, with 4 colours?
Yeah, with 4 colors, it should be fairly easy.
Can't do it.
You can't do it.
You can do it. I'm thinking stupidly, can't you? Problem. So,
I'll do it. You do your own.
scribble on that.
I'm getting lazy.
I'm just going to can I do colour by numbers?
Can
Since I
do
have 10. I can write 1.
What more? The one has to get smart. I'm not sure I'm going to be able to do it that. That's well, see what we're talking about.
Oh, you start with 1 colour.
There is no good way. You have to find your own. I'm just doing it. I'll switch it off so that it wouldn't disturb you. You do your own.
I am.
Just got to read the continent really, because interesting bit.
Welcome to drawing.
We're doing, we're better than mine.
Happy birthday.
Thanks. Oh, happy birthday. The Balkan stuff with us, man.
Oh, you mean the old Soviet Union states?
No, that's not Soviet Union.
Yeah, we recording that. Oh.
Yeah, I'm recording that. Sorry. Sorry, my viewers.
Are we going to do an exam revision?
Not today.
Not today.
We did this at the start.
Okay. Final research.
Yeah, the homework.
Oh.
2, 3.
This unit is so easy, doesn't it?
Ish. Limited tuition, so you can just have bombs.
For me, that's a question.
Doesn't matter.
Probably rational.
I get the same number as the
So, what's the objective here?
You don't have 2 countries with the same.
Only use 4 colours?
Yes.
And they're not allowed to touch
They
each other?
Yeah, no 2.
They share the border.
It's taking a lot.
Well, roughly. Much of the stuff because there's a bit of Russia in the corner. So it doesn't work anyway if the countries are not. Okay, I'll think that now. I think that's enough for me. Oh, and then
I'm pretty much there as well. I'm just doing all the African countries at the bottom that I can see.
oh, why did it switch on?
Why did what?
Oh, it didn't switch on. It switched on. It switched on here. So I got it. Why are we doing this?
Literally, forehead. Question is going to be how would an algorithm?
Yeah, and the answer is nobody knows. So that's what we were looking at, talking about last week. Remember, P is polynomial, NP is non-deterministic polynomial, not polynomial, definitely. It's non-deterministic polynomial. And
Why I've not wrote any of this down, so I don't know how to write it.
maybe you just understood everything.
Sat there nodding.
Yeah, you can finish that at home.
It's the only homework John's going to do.
Okay.
Yeah, that's right.
And the way of thinking about it is when you're given an additional amount of information and the amount has to be polynomial in terms of the size of the input, then you can check the yes answer. Okay. So we had some examples of problems like this, which were the Hamiltonian cycle problem and some other problems, some other graph problems. And so this is this problem in NP to color? Okay, well, so first of all, you can only be in NP if you're a decision problem. So a decision problem means the question is a yes/no question. Okay, so the question can't be color it. What is the coloring? The question has to be something like, so in this case, you could have a question: is it possible to color this map with 4 colors? Okay, or using no more than 4 colors. So that's the setting, and yeah, you can see that this coloring problem is in NP, because if the coloring exists, then I can show it to you, and that's easy to check that it actually is a coloring. So that's quite simple. What we have here is actually the modern formulation is not with coloring maps, but with coloring graphs. So you're trying to color the vertices of a graph. And if there's an edge between 2 vertices, they have to have different colors. Okay, that's how one would put it in today's language. Let's call it K coloring. K is a number. In our case, K was 4. K coloring means to every vertex you assign 1 of K colors. And a proper K coloring means that if the vertices are joined with an edge, called adjacent. Adjacent means there's an edge between them. So if you have 2 vertices that are adjacent, they have to have different colors. Okay. Now, the 4-color theorem is quite a famous one. It asserts that if you get a graph that you can draw in the plane without crossing edges, which is the same thing as a map, really, because what you can do with the map is you can put a vertex on every country, and then if they share a border, you draw the edge that just crosses that border between the 2 vertices for the countries.
As long as there's 5 countries touching in one place, that makes it
okay. So it says that you can always, how can you, okay. So the thing is, with the countries, you have to say that if they're only touching in a corner in one point, if they're only sharing 1 point, then they're allowed to have the same color.
Meaning if it was like 2 square edges touching very corners, that would be acceptable. Yeah.
Like that.
Oh, like that.
Sort of like that.
So like that, the opposite ones can have the same color, and those opposite ones can have the same color. Only if they're sharing a line border, they're not allowed to have it. And in that case, if you impose a condition like that, then 4 colors always suffice. So there's
What if it's an island in the middle of a river between 2 countries that switches allegiance every 6 months? That's a thing.
I know. That's why I laughed, because it was.
I think that you need an animated GIF to do it. Okay, so that's the theorem, which is quite nice. So that's why I put the Wikipedia. Well, it's easy to find without.
I looked at that the last.
And it's quite. It was quite for quite a long time. It was an open problem. So people thought that 4 colors were always enough. From about the 19th century, 18th maybe century, and I think it was about 1970 something. It was proved that it actually is the case, but some people don't trust the proof because much of it is done by computer. Just kind of the proof goes. If it was not possible, then one of the following 157 configurations would have to fail, and then they put those configurations into the computer, and the computer checks them. Well, not exactly 157, but thereabouts. Okay, that's a very interesting thing. However, from our computational point of view, you can turn it into a computational problem where the K is fixed. So you're not asking about how many colors you need, but you're just doing a yes/no question. It's a decision problem. Okay. And the decision problem takes a graph, and it asks whether you can properly K color the graph. And yeah, and the K can be anything. Okay, so this question for any K, so for any K, it's a different problem really, and it's always in NP. Because if the answer is yes, you can k-color, then it's easy to check the coloring. If I give you the coloring, which is not much extra information in terms of volume, so it's polynomially matched because you only get one color per vertex. So it's not much information. So the k-coloring gives you the simple polynomial size proof, and you can check it because you look at any pair of vertices, and if there's no edge, so if n is the number of vertices, so you look at any two vertices with no edge, they're fine. If there's an edge and they have different colors, they're fine. And if there's an edge and they have the same color, then you say, oh no, that's not it. So you can check whether it is a proper coloring or not quite quickly, but not one time. And thing is, if you reduce the k to 2, then you can actually find the polynomial sum algorithm. Okay. It's an exercise. It doesn't go. And if k is larger than 2, it's like 3, 4, 5, or more, then nobody knows the polynomial sum algorithm. That's why I said I'm not sure I'm going to be able to do it, because even if you get a planar graph, deciding whether it's four-colorable is always four-colorable. So that's easy. But even finding the coloring is not so easy. So so to actually do the coloring, it's quite a hard problem, and there is no easy algorithm that you could follow and always get. Okay. So that's an example of a thing. That finishes last week's lecture, basically. So now when we switch to this week's lecture.
Only 42 minutes into this thing.
Is it week 21? Oh, so we've got some time. Okay. You were actually ahead of time, but then I spoiled it all with coloring maps and stuff. And actually properly explaining how you do the binary search. Anyway, so yeah, that's an example.
What to do in England in the proper colour.
Oh,
England is getting in the west and the north.
I thought Ireland had to be green. Not England.
I've always seen England's green, I don't know why.
But Iceland's got to be green.
It's in the eyes.
Okay, so I'll, because we don't have much time, I'll use A, B, and C for the logical, what's it called, proposition that Alice, Becky, and Claude are coming to the party. So A, B, and C can be either true or false, 1 or 0 if you want.
Yeah.
Okay, they're logical variables, or Boolean variables, or binary variables if you like. They're kind of, you can all think of all these things as okay, so Becky will come only if Alice is coming. And I'm trying to write it with ands and ors. Okay, so the first thing, number 1,
So
Becky will only come if Alice is coming. So what we get is, sorry?
if A is true,
Then B is true.
1.
Yeah, I'll just do A plus B is 1. But,
Okay, but I don't want to write it as binary integer constraints. I want to write it as logical formulas. Okay, so the logical form, and I also, so what I could write is, so Becky will only come if Alice is coming. So if Becky is coming, then Alice must be coming as well.
So yes, the nice arrow.
Which in fact is equivalent to, well, either Becky is not coming, so not Becky, or Alice.
Yeah.
So I want to write it as a disjunction, which means only using ors, each of them. The second one is Alice and Claude can't both be invited, which means that either Alice is not there or Claude is not there.
So not Alice or not Claude.
Yes.
That's what that means. Okay.
Which is the same thing as not Alice and Claude. But I want to write it as a disjunction for a good reason.
I prefer that one.
Which one?
The second one you did.
Yeah, it's yes. I prefer the first one for a very good
For a
specific reason.
Yeah.
This is 2.
So one
This is
also
3.
don't need to be invited. So this is an or statement again. Well, and or, because it says so one or both.
Yeah.
So would that be?
So that's
Is that the answer
B
of the upside down
or
bit?
C. Yeah.
Or does that do you say? Is there any alternatives to that?
Yeah, but they're all kind of silly.
Yeah.
You can't make it any simpler than that.
Then that. Okay. And then Alice and Becky have
So
access
you can rewrite everything. You could rewrite it as an implication, like, for example, you could rewrite it in many different forms. You could say that if Becky is not coming, then Claude definitely must be coming.
Yeah.
Or you could say if Claude is not coming, then Becky is definitely
has to
coming.
go. Yeah, yeah.
Or you could say that it cannot happen that Becky doesn't come and Claude doesn't come. Okay. And you can continue like this, make even longer sentences. That, okay.
So not Becky and not Claude.
But what I'm looking for is as simple as possible, and in the form of just a disjunction. So just something or something. Okay? Or negations are allowed, and ors.
Well, that one's implied. Number one, isn't it? B implies A. So Becky will only come if Alice is coming. It's that bottom. The bottom also is just A or B. I was going to say,
That's
yeah,
just
it's
A
got
or B,
B.
yeah. Okay, so that's the good one. So now I can write the formula. I'll call it, even though I usually call it with Greek letters. So it's not B or A, and not A or not C, and B or C, and A or B. Oh, well, I was going to say something about the graph coloring, but I didn't. Shame. It looks like, okay, so well, if you don't mind, I just want to say 2 more sentences about graph coloring. So it's graph coloring looks like it's just a game of some sort, but it's actually a good model for various other problems. So for example, one that is often mentioned is when you have some transmitters or mobile phone stations or something like that. You know, the problem is even more difficult on this. You can, sometimes they're in conflict because they can see the same place from the same transmitter. You know, so you're carrying your mobile and it needs to communicate. Okay, and it needs to agree on the frequency on which they communicate. So they're doing it somehow dynamically because it's changing. But at the heart of it, it really is a graph coloring problem because the vertices will be the different stations, and you can't have the same frequency talking to the same phone from 2 different stations because that would interfere. You wouldn't know who you're talking to. So you're assigning the frequencies to the transmitters, basically. Or you can do it with radio stations. You assign frequencies, and if they see each other, in some sense, then they can't have. Then you put an edge, and it means they can't get the same frequency. Or another thing that you can model using graph coloring is
where there are other sort of conflicts. So, for example, when you're doing timetabling or any kind of scheduling, the jobs that yours is more difficult. So, so for example, when you're doing I don't know, exam timetable, you put for every unit exam, you could create a vertex in the graph, and then you put an edge if they can't be in the same time because they share a student or they share something else. And then you're trying to, and the colors will be the available slots. So a slot could be time, day, and place. Something like that. So that's they're kind of it's a very useful model of graph coloring, even though it sounds helpful and so. Okay, I wanted to say that. Now I've said that, you can go back to it's a bit of a mess. First I got the algorithm wrong. Anyway, so this is what's called a CNF formula. CNF stands for conjunctive normal form, as you see on your next slide, which you can't see here yet. But and CNF means that you've got these brackets. Each of them is a disjunction, so it's all of things, and things are the variables or the relations. And it's a conjunction, so an and of all the brackets, and that's called CNF, conjunctive normal form. And there's an important problem in, these are just the definitions, you read the definitions, then, but the computational problem here is, it takes a formula like the one we just had, and the question is, can you put trues and falses on the variables in such a way that the whole thing would be true? So yes, my question, is it possible to put trues and falses on the A, B, C's, well, whatever the variables are called, in such a way that the whole formula would evaluate it. So, for example, oops, no, I don't want to go forward, I want to go back. So, as an example here, I've got this formula phi. Is this formula satisfiable? Can you find trues and falses for A's, B's, and C's?
Obviously, it doesn't consider, you don't have to have everyone wording it. You just need an answer at the end of it, which will allow something.
So I think, sorry, you need that. So is it possible? So the question is it possible to assign true and false values to A, B, C in such a way that the whole formula would be true?
Yeah.
Okay. So for example, A and B are true, and C is false. I think works.
The first one.
Yeah, vice versa. A and B false seems true. Oh no, you need
no, you need it A and B to be true. So this is satisfied, A or B. This is satisfied because of B. This is satisfied because of C. This is satisfied because of D.
Yeah.
Okay. Right.
So each of the clauses is satisfied, and that therefore the whole formula is true.
Yes.
Huh.
Any questions? Out of time.
Any questions? No, too late.
All right. So we've looked at two important problems which are almost similar, because it's almost like you're satisfying a certain thing where there are constraints, and the constraint is these two can't be the same. Here there are constraints which are expressed like this, and you have to satisfy them all. There will be an and of the constraints. So it's kind of
Doesn't like it.
Nothing.
We're scaling it up a bit.
yeah.
Making it an incredibly large decision variable.
And they're very important because each of them is, and we'll do the machinery next week, each of them is a hard problem to solve computationally. Unless, with the graph coloring, if you only are using two colors, then you can solve it quickly, and that's one of the exercises in the homework. And here, if you have only two variables in each of the clauses, then it's also so that you can also compute it quickly. Otherwise, it's a hard problem. No nutrition algorithms are known. But on to that next week. Someone mentioned revision. Yeah, revision is